Good morning. This is the second lecture in the series. In the first lecture, we have looked at an introduction to light and lasers, mainly light, and a few words about how laser is different. That's where we left. We talked about the nature of light, how light originates, the basic process of absorption and emission, which are crucial to any light source, including laser. We looked at the sources of light and laser as a source of light emission with special features. That's what I meant there. Laser as a source of light with light emission with special features, and laser as an oscillator. This is what we have seen yesterday. Today's class has the following learning objective. You will be able to distinguish between spontaneous and stimulated emission processes. You will be able to recognize the need for population inversion in laser action. You will formulate the rate equations in multi-level systems, describe the working principles of the main laser systems which are available today, and we will continue this in the third lecture. That's the plan for today. Okay. In the first lecture, I had concentrated more on light and the processes of light emission, and I just mentioned something about the why laser is different and laser is the light fantastic. That's where we start. This is actually a quantum mechanical topic. Laser is a quantum mechanical device, a quantum electronic device. So one needs ideas of quantum mechanics to really describe it thoroughly. What is called the Schrodinger equation and time dependent Schrodinger equation are required to understand light matter interaction. But we shall not go that deep. I will give you the necessary level of quantum physics, and we will manage with the essential level of at your level. Later, some of you may do courses on quantum mechanics and then you will understand it more clearly, but we will have a complete picture based on elementary ideas of quantum physics. The first idea that we start with is the following: light absorption and emission. The first aspect of light matter interaction is light is incident on matter, and what happens then? You know, it can cause absorption, you will see it can cause emission, it can be scattered, it can be reflected, it can do nothing and just pass through. It's actually not doing nothing, but that's a different topic. So let us look at the first process. You can see an energy level diagram. We are assuming Bohr-like energy levels. You know Bohr's theory, you all heard of Bohr atom model. So according to that, an energy level system is what you see. For example, you can think of as a hydrogen atom. Of course, hydrogen atom levels cannot give you laser action. We will see later why. So let us assume an atomic system, typical atomic system like a hydrogen atom. You have the various energy levels. You see an atom or an electron at the ground state. It could be an atomic system or atom or electron. Let's say electron, because in Bohr atom model we talk about electrons. So you have what does this picture mean? The picture means that an electron is at the ground state. It has some value of energy, just like your minus 13.6 by 1 for the hydrogen atom. When will it undergo a transition? When light is incident on it, they're of the right frequency, as you can see below. The energy between two levels, E1 and E2, let us call them E1 and E2. If the difference between E1 and E2 is, which you call as delta V, if that is exactly equal to hc by lambda, at that particular lambda, that particular wavelength, or it is equal to h nu, at that particular frequency, we will have an absorption, process of absorption. That is what is depicted here. That is the first fundamental process which is important for laser emission. What is the reverse of this process? That is an emission process. For an emission to happen, the electron should already have an excess energy. Somebody should have put the electron in an excited state, which means the electron has more energy than what it would have in the ground state. We call it E2. Now what will happen to this electron? After some time, according to a rule which we are going to see, this particular electron will get de-excited. People use the word jumping and electron levels and all that. That is a bit crude. There is no level and the electron is not climbing a staircase and it is not actually jumping. Those pictures are rather crude. So we will say that the energy of electron becomes smaller than what it is. It becomes E1 from E2. So you can visualize it as a jumping from an upper level to the ground level, but remember at the back of your mind that it's not actually jumping anywhere. Its energy, it gets de-excited, you can say that. Its energy has become smaller. Then what will happen to the excess energy? Energy is conserved. This excess energy, E2 minus E1, will now be emitted as a photon. This is called emission and we will call it spontaneous emission. Why spontaneous emission? Because nobody is forcing it to emit. There is no external agency which is causing this. By itself, it gets de-excited. Normally, all of them like to be in the ground state. Now, because of the de-excitation, it has come back. So, it would like to come back to the ground state. This process is called spontaneous emission. Now comes Einstein and he talks about a new kind of emission and that is the heart of all that. I mentioned in the last class, the genius of Einstein is in placing the emitter in a cavity. Just now we talked about spontaneous emission. So, there is no external agency. An atom is left to itself, an electron, and then you send a photon. The photon is absorbed by the electron, just like the Bohr transitions, and the electron gets excited. It gets more energy than that it had in the ground state. That was absorption. And then I said spontaneously, after some time, it will emit the photon and get back to the de-excited or ground state. And that happens automatically without any agency forcing it. That is what happens normally. This is called spontaneous emission. Now what Einstein said, suppose we put this atom in an optical field, in an electromagnetic field, what would happen? That is what Einstein asked. People knew about absorption processes, emission processes, spontaneous emission processes. People knew about black body radiation on the one hand. On the other hand, people also knew about cavities. What is a cavity? A cavity is some device to hold some electromagnetic energy or any kind of energy. So there are two branches of knowledge parallelly, one about the emission, the other about the cavity where you can store the energy. Einstein puts them together. He says, let us put the emitter inside the cavity. What will happen to an emitter if it is inside a cavity? What is the difference here? There is a flux of photons inside the cavity. There are photons available. And what happens when a photon interacts with an excited state, atom in an excited state? That is the question. To understand that, as I said, one needs quantum mechanics, statistical mechanics, both these theoretical subjects, but laser is a very practical idea. So behind any practical technology, engineering or practical device, there is a lot of deep theory. We have electromagnetic theory, quantum mechanics and statistical physics. Of course, optics, which originated out of electromagnetic theory. All these branches of physics contributing to this light fantastic. So let us see what happens when Einstein put the emitter in a cavity. There is a new kind of emission. What we said so far is spontaneous emission, and now we have a new kind of emission. Let us look at that. The new kind of emission. This is called stimulated emission. Why is it called stimulated emission? Because you can see an agency here which is stimulating this. If you remember in the previous pictures, spontaneous emission, there was no agency. Automatically, the atom got de-excited. Now, the excited atom interacts with a photon, incoming photon, because there is a photon field. We keep it in a cavity, and in the cavity there are photons. So this photon interacts. Where did this photon come from? For any material, if you give Avogadro number of atoms, there will be some of them emitting at any temperature. So one of those can act as the source here. Just like in an oscillator, any aspect, any part of noise can be picked up and it will be amplified. Similarly, here any one of the stimulated, one of the spontaneous photons can do this business of stimulation. So we have again an electron at an excited state and it is interacting with a photon. So, there is a new process which also is an emission. And what happens when it emits? Of course, there is this excess energy delta E, E2 minus E1. That excess energy also gets emitted as a photon, satisfying the condition H nu is delta E. So, now we have two photons coming out. Input was one photon, output were two photons. So, we should clearly distinguish between the various processes. And the most important thing for laser is this particular photon, stimulated emission, which comes out of stimulated emission, is exactly in phase with the original photon. Whereas in the case of ordinary emission or spontaneous emission, there is no phase relation between the various photons. In one event of spontaneous emission, there is only one photon, but there are a number of atoms in a system. So there will be a large number of stimulated, a large number of spontaneously automatically emitted photons. They don't have any correlation with each other. Of course, they will be of the same frequency because all of them have to satisfy this condition. But here there is something more. It is of the same frequency, but a stimulated emission results in a photon which is exactly in phase with the original photon, which causes the stimulated emission, and that is a main point in laser, which is made use of in laser. Let us look at this process in a little more detail. What happens when you have this atom emitter in an optical field? So, you have here, let us look at the process. First, before emission, the atom is already excited before emission, that is the difference, and then there is a photon interacting with it. As a result, it gets de-excited. So, you see where these two photons are coming from. One was there originally, which caused this process. The other one arose from the energy difference between these two levels, delta E. So, resultant that we have two photons, and both photons propagate in the same direction, exactly same direction. So, what is the difference between spontaneous emission and stimulated emission? Number one, spontaneous emission happens without any external agency. Secondly, the spontaneously emitted photons are in arbitrary directions. They come in all directions. They all have the same frequency, but they travel in different directions. They do not keep a phase relation with each other. Whereas in the case of stimulated emission, the photons are exactly in phase with each other. They of course have the same frequency. They travel in exactly the same direction, and in addition to that, they also have a phase relation, fixed phase relation. We discussed about phase in the last class, if you remember. Phase is the status of motion. If suppose some soldiers are marching, if all of them have their one foot up and one foot down at the same time, they are all in phase. If everybody raises one foot up and only one person puts the foot down, then that is out of space, totally out of phase. When you have dance programs, people have to dance in phase, otherwise there will be chaos on stage. So here there is there is a lot of there is a good correlation between this. Imagine both of them are waves, then both the waves have the same phase. By both I mean the exciting photon and the stimulated emitted photon. Both these are strictly in phase. That's the relation between these two. So now look at light and laser, ordinary light and laser. Ordinary light that you see has been emitted by some processes which we discussed in one of the processes which we discussed in the last class. And photons come in all directions of the same frequency, but all directions and totally out of phase. In the case of stimulated emission, we have these photons of the same frequency, same direction, same phase. So how do we compare this? How do we know, okay, what comes out of it? What is the advantage of this stimulated emission? How exactly is it different? I'll give you an analogy, an example. Imagine a group of soldiers in an army. These soldiers will be able to do something, whatever they are supposed to do, rescue operation or war, They will be able to do that if they are coherent, in the sense they all act in phase, in step. They should follow the instructions clearly in step. They should go according to some plan, and they are able to do all that. An army is able to do all that because of the in step relation between, correlation between their actions. Now suppose the same army has made a big victory and they all want to celebrate, and they are not in their uniform now, they go to normal clothes, civilian clothes, and they go and they want to celebrate, so they go and have some drinks. And how they will behave now? They will not be any more in step. They'll be walking here and there, they'll be talking, they'll be doing various things without any correlation with each other, especially when they're drunk. So that is a difference. A set of drunk people who are doing random things, and the same people in army uniform marching to in step. That is the analogy which I want to give you. So which is the army and which is the drunken set? The set of drunken people here refers to ordinary light, and the army refers to a beam stimulated, beam coming out of stimulated emission, which we will see is a laser. That is the difference between laser and normal light. So I am not telling normal light is useless, normal light is useless or something like that. We are all very happy to have normal light in the world. We are able to see each other and all that because of light. Only thing is, if you want to do some very specific things like drill a hole in metal or treat your eye if the eye has a problem, for that this kind of light is not used. That is the analogy between the ordinary light and laser light, and that is why the engineer or the technologist or whoever is using, even the doctor who is treating your eye, they would like to call laser as a signal and ordinary light as a noise. Signal is what you want for a particular specific purpose. Noise is what you don't want and what is working against the signal, or it is making the signal inefficient. That is called noise. In electrical engineering also we use the same terminology. So this is what is to be understood, the difference between ordinary light and laser light. Ordinary light arises out of spontaneous emission and scattering and things like that, and as a result of it, what you have are photons, of course, but of different frequencies, because there are different sources which have different delta E's in them. For a given process of spontaneous emission, yes, it has got a specific frequency, and if you are from the same set of two levels, you will have the same frequency coming out. But they go in different directions, arbitrary random directions, and they do not have any phase correlation. Whereas laser emission comes from, is a result of stimulated emission, and we have correlated photons, phase correlated photons. They are called coherent, and they are also monochromatic, which means they have the same frequency. That is a major difference between these two. But what I want to highlight here is the basic process from a quantum physics point of view. What is the difference between the process of spontaneous emission and stimulated emission? Now the stimulated emission, not only the stimulated emission, but all these processes, absorption, emission, all of them are described by Einstein's coefficients. The rate is governed by Einstein's coefficients. Let us look at what are these Einstein's coefficients. You look at the energy level diagram. There I have written absorption, and I have depicted a process of absorption. The ground level has got energy E1, and there are N1 atoms in the ground level, atoms or electrons, whatever. So let's say electrons, N1 electrons are sitting in the ground level, which means N1 electrons have a given energy. They are not actually sitting somewhere. Now you have a photon coming from somewhere, and that photon interacts with the system. As a result of it, this gets excited, which means the energy of these electrons goes to the next level. They get excited. This process is governed by a coefficient called B12, B suffix 12. That is the Einstein's coefficient, which describes absorption. What is this B12? What do we understand by that? That is written here. What I have written is a rate equation. It's a differential equation. don't get frightened by that, I will explain what it is. It talks about the rate at which N1 increases or decreases. In this case, it is decreases. What is N1? N1 is a number of atoms or number of electrons in the ground state. N1 changes with time. First point is N1 changes with time. So we can talk about a rate at which N1 changes with time. In calculus, that is given by dN by dt. I have put a word absorption here to denote absorption process. So we have this rate at which N1, the ground state atoms decay or change, the population of the ground state changes at a rate given by dN by dt with time. Now Einstein describes that this is equal to minus B12 N1 U nu. U nu is the spectral energy density as I have defined it, and N1 is a number in the ground state and B is the proportionality constant. So what it says is the rate at which the number decays is proportional to the number already present there, N1, and it is proportional to the energy density which is causing it. The proportionality constant is given by B12, the Einstein's coefficient B12. There is a negative sign there which says it is a decay, in the sense the number decreases. Most of the atoms are in the ground state to start with at any temperature in equilibrium. When this process happens, there is a photon interacting with that, then the photon excites some of the electrons from the ground state, which means N1 now decreases. That is what we are describing. Let us look at the equation once more. N1 decreases because some of these electrons get excited because of this energy, excess energy coming in. They take that energy, and it's a one-to-one process. One electron takes one photon h nu, that much energy, and goes to the excited state. Then another one takes that and goes to the excited state. So that means N1 is decaying, N1 is reducing with time, and that change rate is given by dN1 by dt. Einstein said that is proportional to the number already present at any time. There is a very interesting type of decay which you find in science and engineering very often. The rate is proportional to the number already present there and the energy density, and the proportionality constant is defined as B12. Then there is a negative sign telling you that N1 is decreasing. Originally there was some number, and after some time that number has decreased. That's what it means. So this is how Einstein describes absorption process. But we have to go further and look at the other processes as well. Please note that there is a U nu sitting here, which means this is the energy density of the incoming photons. So this is also called pump. We will call it pump in future. It is like pumping water up to the first floor. That kind of pumping means providing the energy required. For example, water to go from the ground floor to the top floor. So that is why it is called a pump. Literally, it is called a pump. So we have a pump intensity sitting here. So this is the first process. Now Einstein describes the second process. I have put both the processes here. The second process is spontaneous emission. What is the process here? I repeat, a photon interacts with an atom which is already excited, and this is spontaneous emission, right? Spontaneous emission is because this is already excited. A photon causes an atom or electron to be excited, and the photon has done its job. Once the atom is excited, the photon is no more there. The photon has given its energy, transferred its energy to the atom in the ground state. The atom has taken that energy, the photon is no more there, and then it gets excited to the excited level E2, by which I mean its energy becomes E2. It was E1, it has taken h nu, now it has become E2. That is absorption, pumping, and then what happens is, as I said, automatically, without any external agency, without help from any external agency, it gets de-excited and it comes to the ground state. Now Einstein says that rate is given by this equation. Let us look at this equation carefully. This talks about N2. What is N2? N2 is the number of electrons in the excited state. Why does that number change? That number changes with time. That's what the equation says. Why does it change with time? Because some of them have got spontaneously, and some of them have got spontaneously de-excited and they come back to the ground state. So N2, some number at any time, after some time, if this process is the only process happening, then after some time this number will decrease. So again we have a dn by dt which is a negative number, and that is proportional to N2, the number already present. If nothing is sitting there, there is no spontaneous emission, so that will not be there, and there won't be any such process. So you have, this is a rate, this is a time rate, and number decreases, the negative sign says N2 is going to decrease, and it is proportional to N2 already, and the proportionality constant is given by A21, Einstein's A coefficient A21. Now look at the difference between these two processes. Look at the equation. The equations are simple enough, I have explained it thoroughly. So look at this expression and this one. There is a B coefficient sitting for absorption and an A21 sitting here. 1, 2 means from 1 to 2. 2, 1 means from 2 to 1. That's the meaning of this 1, 2 and 2, 1. And A for emission and B for absorption. That is the notation which Einstein used. Okay. Once again, B for an absorption process, A for an emission process. 2, 1 means from 2 to 1. 1, 2 means from 1 to 2. That's what it is. And there is a, this is called spontaneous emission. This process is a spontaneous emission process. What is the other process? We have 3 processes: absorption, spontaneous emission, and stimulated emission. So let us look at the third process. Let us look at all the processes together. Okay. So we will go by step. First, absorption that we understood, V12. Then we introduce spontaneous emission. We have A21. Now I put these pictures along with the new process, which is the third process. Now focus on the third process. The third process is the new process proposed by Einstein. It says the atom is already excited and a photon is interacting with it. In the case of spontaneous emission, atom by itself gets de-excited, whereas in the case of stimulated emission, it gets de-excited upon interacting with a photon. There is an input photon, that is the difference. Now let us look at what is happening here. So N2 will decay according to this. There are 2 channels for N2 to decay. N2 number in the excited state will become smaller because of this process, spontaneous emission, also because of this process, stimulated emission. So we have to write another rate equation, one more rate equation for N2. When I write the rate equation for any of these processes, I am assuming only that process is happening. If both processes are happening, we will include both terms. We will do it later. So right now let us say if only this process is happening, then N2 will decrease. The decrease of N2 will be described by an equation like this. First we have dN2 by dt, which means N2 is decreasing, N2 is changing with time, and we are looking at the rate at which it is changing. I have put STIM here for stimulated emission. This is negative because this process leads to is taking away atoms from N2, they are taking away, reducing the number N2. So that is why the negative sign, and it is a B process. I denote it with the B. Einstein denoted it with B because it is an emission process. And this one, then here what we have, this we have an N2 here and the union. Please note that this B21 and B12 are different from A21. This spontaneous emission is A21, stimulated emission is an emission process, but it is called B rather than A because B21 and B12 are correlated. That is an important point. So he calls it, this is an emission, but he calls it as B21 because it is opposite of B12. That is how it is defined. So A for only spontaneous emission. A is not for all emission. A is only for spontaneous emission, and B for stimulated emission, and B for absorption. Why? Because they are opposite processes. In one case, it takes a photon and goes from 1 to 2. In this case, it takes a photon and goes from 2 to 1. This photon induces it to go from 2 to 1. So the emission, spontaneous emission is A, and stimulated emission and absorption both are described by B, the letter B, Einstein's notation. Now, there are two photons coming out of this, and this is a new process. So, please compare without any confusion all the three processes. Einstein has two coefficients, A coefficient and B coefficient. A coefficient is emission, as I said earlier, but B coefficient is not only absorption. Earlier we saw B represent absorption. Now we see that it also represents stimulated emission. Why did Einstein choose it like this? Because B12 will refer to a transition from 1 to 2, and B21 will be a transition from 2 to 1, and that is different from the spontaneous emission. That is why he called it as a B rather than A. Now you may see that A12 is missing. Why is A12 missing? It turns out that B21 is equal to B12. You can prove it if there in any of the textbooks, but in a few lectures we can't go into that detail. So, all absorption is stimulated absorption only, and there is no spontaneous absorption. That is why B21 is equal to B12, but A12 is equal to 0. Okay, we have only A21, not A12. How do we understand this? A is spontaneous emission and B is absorption. How does absorption happen? For absorption to happen, you need to supply that much energy. Then only the atom can take the energy and get excited. So you need an external agency here. Okay, so this is so it has to be stimulated. What do you mean by stimulated? Stimulated means caused by an external agency. Just like this emission is caused by this external agency, the external agency here is a photon, incoming photon. Absorption has to be anyway. Somebody has to give the energy. If a system has to go from E1 to E2, somebody has to give the energy. So it is always stimulated. Or in other words, there is no spontaneous absorption. An atom sitting in E1 cannot by itself go to E2. That is why A12 is missing. We have only B12 and B21, which are opposite to each other, and A21. A21 is spontaneous emission. The opposite of that will be A12, which is spontaneous absorption, which does not exist. That is the main point here. So you see that the rates of the three different processes, absorption, spontaneous emission and stimulated emission, are governed by Einstein's coefficients A and B. They actually govern the rate at which it is happening. These equations are not complicated. We have understood it in a step by step manner. How do you get any particular N1 or N2 from such equations? You have to integrate it. Integrating this will give you the actual number, but we will not do that now. So one point here is that I have assumed in all that there is only one energy level. I have shown a lot of energy level diagrams. Only one energy level exists at each value E. E1 is only one level I have assumed. E2 means only one level I have assumed. You will see in some books, or you will hear later, there is something called degeneracy. Degeneracy means corresponding to the same level, same energy, there may be different levels. Okay, minus 13.6 by 2 square, let us say. Suppose there are two such energy levels which has exactly the same energy. That is a special case, and in atomic physics it is called degeneracy of levels. Here, for simplicity, I am assuming that there is no degeneracy. In fact, in reality, some of the levels have degeneracy, in which case there will be a factor which I have not included in this rate equations, because we want to understand from the simple and fundamental level. That is one thing, approximation which you have made. Now let us look at a two-level system, a two-level energy system. There are no two-level systems in the world. Even Bohr level, there are so many levels in a Bohr atom. Hydrogen atom also has got several energy levels. But let us, to understand the process, let us look at an ideal two-level system. It has only two energies, E1 and E2. N1 atoms are there at a given temperature. N1 atoms are here, and N2 atoms are excited. The question is, what will be the numbers like? What will be the fractions like? How big is N2 compared to N1, or N1 compared to N2? We know that N2 will be small, intuitively we feel that N2 will be small, but how small? How do we actually decide? At any temperature, it is governed by temperature. So at any temperature, how many atoms are there in these levels? That is governed by this equation which is given here. That is governed by two